All right, guys, so we're continuing on with this review. Now we're on to problem number 5, which deals with projectile motion. So we got a ball being launched from a height above the ground, and it's being launched at an angle, and it's going to undergo projectile motion. So with projectile motion problems, you can just draw kind of the trajectory. That's a good enough idea of what's going on. We need to start by finding the components of the initial velocity. So for part A, we're going to find Vix and Viy. So this is a little bit of trig. So we have our angle of 10 degrees here, and we're looking for how fast is it moving across, how fast is it moving up. So Viy in blue there, and Vix in green. The velocity here is 10 meters per second. And this is theta, which is our angle in degrees. So Vi overall and theta. As soon as you see theta, you're going to have to do trig. So it's Vi cosine of theta and Vi sine theta to get the values. You look at the picture to decide if it's positive or negative for their signs. So for x, it's going to the right, so it's going to be positive, and it's 10 cosine of 65. I probably didn't draw that angle big enough, but it's okay. It's just a sketch. Viy is also positive because this time it's moving upward in the y direction, and it'd be 10 sine of 65. So you're going to get similar kind of doing components here. You should get rounded 4.2 meters per second positive for the x and a positive 9.1 meters per second for Viy. At that point, then you can start filling in your tables. So we have our y chart and our x chart. So for the y's, it's our normal free fall chart with delta y, Viy, Vfy, g, and t. For the x direction, it's simplified because x is constant. So those are those values. We're going to take 4.2 and put that in for Vix, and we're going to put 9.1 meters per second for Viy. Be careful with that. Again, people have a tendency to put 10 in somewhere. Don't do that. Gravity's still negative 9.8, so we know that. Meters per second squared. The ball starts from an initial height of 8 meters, so y initial is 8. It's going to go all the way to the ground, so the final y position is 0. So that's going to be a negative 8 meters for delta y. We're looking for a couple things. So we're looking for how long was the ball in the air, so we're looking for time. So I think we can solve for time using that equation. And then we're going to take that time and plug it in here, because as it's going up and down, it's also moving across. And we're going to solve for delta x, or how far it moves in part B. Part C, because A was up here. So part B, we're looking for the time. Part C, we're looking for the displacement horizontally. So, so for part B, I want the equation without Vfy. So we could do that. I'm going to show you what happens. So I'm going to, again, remind you of a workaround that we've talked about already. So if we use the equation without Vfy, we get delta y equals Viy delta t plus 1/2 g delta t squared. This is going to be problematic. Just I'm going to show you the numbers. So negative 8, 9.1 delta t plus half of negative 9.8 delta t squared. Again, I can simplify this. Negative 8 equals 9.1 delta t, and this would be a plus a negative 4.9 delta t squared. But this equation mathematically is a little bit challenging to solve. It's a quadratic. So you could use the quadratic formula if you really want to. I don't like the quadratic formula. I generally do something else. So this is my workaround for this. So instead of solving for Vf, oh, actually, I'm talking about a question. We didn't solve for Vf at all. We want time. So yeah, so we would solve for time. Sorry, originally when I designed this question, it was a little bit different. So we're going to solve for time without. Oh yeah. So yeah, I'm right. So this is one where we don't have it. So what I'm going to do is I'm going to solve for Vf. So I'm going to not solve for time. I'm going to solve for Vf. So I want the equation for Vf without time. So that's the squared one that we've used several times in this video. And once I get Vf, then I can plug back into a simpler equation and get time. So it's like a way to avoid the quadratic formula. So I don't like the quadratic formula. I try to do it a slightly different way. Again, there's lots of different ways. If you feel confident in the quadratic, do that. All right. So Vf, we don't know. That's what we're looking for. VI is 9.1. We got to square that to negative 9.8, and we have a negative 8 for my displacement. So when I plug into that, I will take a square root of both sides. And you get VF is equal to, and your calculator just tells you the positive, 15.5. So this is VFY, just to be clear. So 15.5, we got to think about, okay, when it gets to this point, when it's getting back to the ground, is going up at 15.5 or down? So it should be down. So this is a negative value. So negative 15.5 meters per second, that's the value for VFY. And then now I'm going to put in that for there, and then I can solve for T much simpler. So if I do the next part, VFY equals VIY plus G delta T, now I can go through and get this much simpler fashion. 9.1 is my initial there, gravity is negative 9.8, and delta T. So I'm going to subtract 9.1 from both sides, and I'll get something like 24.6, sorry, extending. 24.6 negative equals negative 9.8 delta T, and then it's just doing the algebra. And you'll get the time that it spends in the air is 2.5 seconds, or about that. So again, slightly rounded, but that's good enough. So, so instead of doing the quadratic and getting a small number and then 2.5 for your second number, because it actually is going, it's down there a couple times. So you're gonna go through, and this is it's a two-step process. So first you got to solve for VFY, and then you're going to use VFY and to be able to solve for T. Once you get T, part C is very easy because there's only one equation in the horizontal, so it's delta x equals VIX delta T. So it's going to be delta x is equal to 4.2 times 2.5. So you get delta x is approximately 10.5 meters. Okay, so again, you're just taking that up into this chart, plugging in 2.5, and then multiplying the two numbers. So again, I try to avoid the quadratic. I don't like doing quadratic. If you want to do the quadratic, that's perfectly acceptable. You just have to show your work. So again, you would do the quadratic formula, which is like the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. That's what your time value would be equal to. Again, you got to choose which root makes the most sense. I think one of them would be negative, which wouldn't make sense because it would be negative 8 down here. So if this is time equal to 0, it's before that. And then the other one is when it's reaching here, which is the 2.5 one. Okay, so either of those will work. All right. So we're into the next problem, 6. I think we have a couple more, 6, 7. Yeah. So on this one, this is our centripetal acceleration problem. So there's a car. So I'm going to draw an overhead view. I'm just going to draw a dot for the car. And the car is going in a circle. So that's not quite a circle, but you get the idea. And we know the radius of the circle is 400. It tells you the mass of the car. You don't really care about the mass of the car. You don't need that in your work. But it says that the car goes around the track 5 times. That's how many times it goes around the track. And it tells you the time that it completes that. So I'm just going to say R is 400. So I'm listing out here these variables. We don't have really the same type of chart that we did in the other problems. The time is 160 seconds. And the distance it's going to travel is 5 times, I'm going to just write C for the circumference. Okay. So the circumference of a circle is 2 pi r. So we're going to multiply that by 5. So 5 times C. So that would be equal to 10 pi r. So we can figure out that number in meters. So it'd be 10 times pi times 400. And for that value, I got a fairly large number, 12,566.4 meters. So we're going to use that, and we need to find the average speed. So again, the average speed is just the distance over the time. So it's going that distance, the 12,566.4, divided by the 160 seconds that it takes to go around those 5 times. So if you do that, you'll get an average speed of something like 78.5 meters per second. I did look up some values on the internet, and these are about the right distances for like circular tracks that some race cars go around. So this is still moving pretty fast. Then for part B wants to know the centripetal acceleration. So that's this center seeking acceleration. So this velocity or speed is going forward, but V, so if I call that V for velocity, which is really speed in this equation, the acceleration is pointing inward towards the center. So it always points inward towards the center, no matter where you're at. So the centripetal acceleration that it experiences would be equivalent to V squared over R, and V is our average speed. So it'd be 78.5 squared divided by the 400 value. So if you do that, put that in your calculator, you'll get an acceleration of 15.4 meters per second squared. So that's how much acceleration is directed inward to make this thing go in the circle and stay in that circle. So C and D are kind of conceptual questions, and they're really just based on this equation. So A equals V squared over R. So we're kind of looking at the factors and trying to determine how changing those factors would affect the result. So we have a number here, and we could do it with our equation and figure out how much bigger it is, but we can just use the equation without plugging in those numbers. So this is our initial acceleration, let's just say is at this velocity V and this radius R. So in part C, it says if we triple the speed. So we're gonna do our new velocity, and I'm gonna put a little apostrophe next to V to make it the new one. That's 3 times the original V that we had for V and V squared. So if we plug that in, our new acceleration would be V prime squared over R, and because our radius is staying the same, and that would just be 3V in parentheses squared over R. So if we distribute the squared, it'd be 9V squared over R. We said V squared over R, that's just A. So it's 9 times our centripetal acceleration that we originally had. So that is our new acceleration, new centripetal acceleration is 9 times that. So that's how you kind of do those types of assessments of what's happening if you double or triple something. So in D, it says if the radius of the track is doubled. So we're gonna see how much the centripetal acceleration changes. So again, we're gonna say this is our original one. We have a new one here. We want the new centripetal acceleration, but this time our new radius is doubled. So it's 2 times R. So if we plug that into our relationship again, so our new one would be V squared over R prime. And then we would see that that's just V squared over 2R. If we group this V and V squared over R together, that's this relationship. So I can just substitute back in, it's 1/2 AC original. So AC prime in part D, the new centripetal acceleration, once we've shrunk this radius, is half we doubled the radius, sorry, not half it. We doubled the radius, so the centripetal acceleration has gone down. It should make sense, right? Like, so instead of being 400 meters like it was in the first one, we've made it a much bigger circle. So we've doubled the radius, so it is easier to stay in the circle. It's kind of like if you remember back to driving or riding a bike or something, if you're trying to take a really tight turn, it's difficult to stay in the circle, but if you're taking a long, gradual turn, it's much easier. Okay. So a couple more questions, we're almost done. This one is our vector question. So it says a path through the forest takes the following directions. So we're gonna go 10 miles at 60 degrees above the negative X. I'm gonna label that A as my first vector. B, 5 miles along the positive Y. And then I'm just gonna make C 2.5 miles along the positive X. So the first thing to do is just draw a picture. So I'm gonna start over here where I have a little bit more room, and I'm just making a set of axes. So the first thing we need to consider is 10 miles at 60 degrees above the negative X. So negative X is left, it's above it, and 45 would be in between. So I'm gonna make it maybe a little steeper than 45, and I'm gonna call that vector A. Okay. For vector B, it's 5 miles along the positive Y. So 5 miles, I'm gonna draw in green, and its positive Y is just going up, so it should be about half this distance, and it's going straight up, so that's B. Maybe that's a little longer than half, but it's again just an approximation. And finally, the last one, 2.5 meters along the positive X. So positive X is right, and it's gonna be about half that size again. So that's maybe C. And we want the resultant vector. The resultant vector is from where I started all the way to where I finished. So that's R. And I also want to find my angle that forms. So I'm going to look for theta. So that's what we're doing mathematically when we set up our table and do the work here. So in our table, we have our x direction and the y direction. We have our three vectors, A, B, and C. We're going to add those together and get the resultant, which is R. So again, the first step in these is to just remember, okay, we need to do all the positives, negatives, and zeros. So if we look at just the red vector, vector A, it's going left and it's going up. So that's negative in the x and positive in the y. B is not going in the x, so that's 0. It's going up in the y, so that one's positive. And then C is positive in the x because it's going to the right, and it's not going in the y, so that's 0. So now we're just going to plug in the numbers that are simple, and then we're going to do some trig that would require us to figure out the components for AX and AY. So B is just only going in the y, so all 5 of it is going that way, and for C, all 2.5 miles is going horizontally or in the x direction. So for A, again, just like we did with the vectors with projectile motion, we're going to solve for AX and AY. So I'm going to do it over here. You could put it in the chart, but I just want to have a little bit more space. So it's the length of A times the cosine of the angle that it forms, and then the length of A times the sine of the angle to get the two components, the x and y component. Again, we've already listed out negative and positive, so I can just do the math here. So it's 10 cosine of 60, 10 sine of 60. Cosine of 60 is a half, so half of 10 is 5. Cosine of 60 is about 8.66, so that's going to be 8.6 for that one. So this is 5, and this is 8.6. So the values, when we add the columns, that's the next step. We're going to get a negative 2.5, so it's going left 2.5, and it's going up 13.6. So now we're going to do the last part, but that's what this is saying. So it goes across, that's Rx, and it goes up. And that looks pretty close to my picture or my value, and we're going to use it and make it a right triangle and use the Pythagorean theorem. So R squared equals Rx squared plus Ry squared. This is just the concluding steps. So we got 2.5. If you want to put the negative in, you can. Make sure you put in parentheses, but it's going to get squared away. Plus 13.6 squared. We need to take a square root of both sides of R squared and of all those numbers to get our value for R, which turns out to be 13.8, and it's miles. That's what the unit was in this measurement. The last step here is to get into theta. So theta is the inverse tan of the opposite over the adjacent. We're always going to measure the angle from the horizontal, so the opposite is Ry, and the adjacent is Rx. Again, you don't have to worry about the number or the sign of the number here. So I'm just going to put in the y, which is 13.6 divided by 2.5. If you put negative 2.5, you're going to get a negative angle, but we describe the angle, so you don't have to worry about that. So inverse tan of 13.6 divided by 2.5 gets you a big angle. It's like 79.6 degrees, and that makes sense, right? Because this component is much larger than that one, so it's going up. So that's above. And this is to the left, so up, and then left is negative x. So it's 79.6 above the negative x. So those are my two answers for R and theta for calculating this displacement. All right, so the last question here, this is more conceptual than anything else. And it's just asking you to kind of explain what's happening in these situations or why it does what it's describing as this motion's occurring. So what I want you to do is use these velocity and acceleration vectors and the directions of them to talk about. So for part A, if I draw a picture, there's a ball and the velocity is going up and it's slowing down. So this arrow gets smaller, these are my velocity arrows. So these are positive velocities. So if I was writing the direction of the velocity, it's positive. Which way is the acceleration happening here? The acceleration is due to gravity, that's going down. So A is a negative value. So we have a positive velocity and a negative acceleration. So those two ideas are disagreeing, and disagreeing equals decreasing velocity or slowing down in every kind of everyday language. So the number for the velocity decreases. For B, It's the same scenario, except it's on the way down now. So the ball is falling downward. As it falls, it speeds up. So if we look at that, these velocities, we have negative velocities. Our acceleration due to gravity is still the same direction, it's negative. So we have a negative velocity and a negative acceleration. So they agree. Agreement means the opposite. So if you agree, if the velocity vector and the acceleration vector agree, the number for the velocity increases or gets larger, which is commonly referred to as speeding up. So that's what I mean to explain these. The last two, C, there's a car. So I'm gonna put the car facing right. So there's my car. And the car is backing up. So the velocity is going in the negative direction. And it's slowing down. So these arrows get smaller. So in order to slow it down, we would have to apply a force going the opposite way. So my acceleration would go to the right. So again, we have a negative velocity and a positive acceleration. So that's disagreement. Disagreement gives you this number for the velocity gets smaller. Same car this time, still facing to the right. So it's backing up again, so it's got a negative velocity, but this time the arrows are getting bigger because it's speeding up. So in order to do that, we would have to make our acceleration go in the same direction. So we have a negative velocity, negative acceleration. They agree. Agreement means increasing velocity. Okay, so that's a lot of the types of questions that you're going to see on the test. Hopefully, these reviews are helpful.